And to double check, how much time do I have?
So we generally do a half hour of the slide and then a half hour of discussion. Yeah, that's kind of the guideline.
Okay, thank you.
Yeah, so let me just do a quick introduction just so we have it for the recording. So today we would like to welcome Professor Marko Cetina. Marko did his undergraduate degree at Caltech and then his PhD at MIT. He's currently a professor at Duke University, holding a joint appointment in physics and electrical and computer engineering departments. And today we'll be talking about quantum simulation and computing with long ion chains. Thank you so much.
Thank you, Dorota, for the nice introduction, and thanks to Martin, Xiaojun, and Nicholas for the kind invitation to present at the seminar. It's a great pleasure to be here over Zoom and tell you about the work that is really the work of a number of people across different collaborations. It has one common thread of having been done on one long-chain trapped ions quantum computing and quantum simulation platform. This work has been funded for a long time, had been funded at University of Maryland by IARPA, and is more recently funded by NSF and the QSA program, under the QLCI program with Maryland jointly, and under the QSA program by DOE. It gives me a special pleasure to present trapped ion work that's experimental at the University of Washington with a very, very long history of precision measurement, especially with trapped ions under Hans Dehmelt, and more recently by the other trapped ion groups. So I hope that I can give a little bit of insight into some long outshoots and outgrowths of the many decades of trapped ion work. In a very, coming from a quantum information science, in a very broad sense, we would like to get to interesting, both computationally interesting problems that we're hoping our quantum systems can solve, such as implementing force algorithms, and also societally and useful for physics simulations, including simulations of chemistry and simulations of nuclear physics. In order to get there, we will need many more qubits and much lower errors than what have been demonstrated so far in quantum computing and simulation systems. While we are trying to fight these through a number of approaches, which will be the subject, some of which will be the subject of my talk, we do keep in mind that on the way there, we also encounter fundamental problems akin to those encountered in precision measurement, including, for example, scattering laser-based gates, intrinsic micromotion in Hall traps, or even in both ion, atom, and other platforms, effects of, say, black body radiation akin to what you see in clocks. And these will likely present roadblocks at an earlier, at higher error rates than what we really need, especially for some digital approaches. And we're hoping as a community that introducing quantum error correction will help us get there at the cost of many more qubits. And this will be in addition to various technical, encoding, circuit, and analog approaches to scale up simulations. I will also address error correction that has been implemented on this ion platform we'll be talking about. As a summary of the talk, I'll present the trapped ion experimental system, and then several applications, first in simulation in collaboration with, which was well known, on the thermalization of a Z2 lattice gate theory. That's very recent experimental data that we're writing up together with a group of Jorge Davudi at UNT. In another application that was to continuous symmetry breaking in the XPath model in close collaboration with a group of Chris Monroe at Duke. And then examples of analog and digital quantum simulation using the trapped ion platform. I will present a few different ways in which, more or less technical ways, in which we hope to speed up and enable larger simulations. One is by using more expressive gates that instead of just being two-body, based on two-body interactions, like the XX gate, are intrinsically based on many body. The effective gate union is, for example, XX. And another approach, as I highlighted before, would be to introduce error correction into the mix. And I will present a error correction, error readout approach and encoding approach that is particularly suited to highly connected trapped ion and also other atomic platforms. And I will close the talk with some future experimental capabilities that we have developed in the system that we're really looking forward to make use of in simulations, including, say, controlled dissipation and bosoning. The system that I will be talking about was constructed at the University of Maryland, effort led by the group of Chris Monroe while I was working as a research scientist there, and funded generously under the Logic Q program by IARPA, with the goal of realizing an encoded, error-corrected trapped ion qubit. This work provided a blueprint for a great many things that came out, including the starting and training of the initial people who moved over to IonQ. Even while the two efforts at university now at Duke and IonQ have remained separate efforts. This was done in close collaboration with a number of companies funded by the Fed, starting with India National Laboratories, who provided the ion trap chip. And I especially want to emphasize L3 Harris, who built up the individual addressing system based on the 32 channel, who stopped it modulating. If we open this box, that was shown in the previous slide, what you will find inside is a whole bunch of wires at the high level. But looking a little bit more closely, we see our ion trap, produced, as I mentioned, by the India National Laboratories. This is the second generation of the trap from this series, which, after working out some bugs over the first 2 years in about 2017-18, has served us very well since in many projects. We have performed simulations with up to 27 trapped deuterium 171 ions, serving as spins, i-qubit. And this continuous symmetry breaking work that I highlighted previously is the largest simulation we've done of this system. So it's 27 spins. And this trap is housed inside of a vacuum chamber that you can see here. And while seeing a whole bunch of wires in this picture, you can discern, if you see my cursor visible?
Yes, your cursor is visible.
Yeah, thank you. You can see, in addition to the vacuum chamber, you can see other components of the system, such as the radio frequency driving the ion trap, and very importantly, the bottom plate that contains all the optics provided by L3 Harris for individual addressing of the ions. And one aspect that this highlights is that compared to usual AMO systems, this is quite modular. We have a chamber module, radio frequency module, optical addressing module, and so on. And this modularity has allowed much better performance, as well as isolation from the environment in a more compact package, and hence unitary gate performance. As you may know, the qubit that we use, both as spins and for digital computation, is comprised of the two first-order magnetic field insensitive. So we really don't have to worry much about magnetic field stability with this qubit. Hyperfine states in ytterbium-171 in the ground electronics. These are separated by a frequency that is very, very common. In fact, this is one of microwave atomic clocks that is used, including in space. But instead of driving it with very stable microwaves, which we can do, what we actually do is we use a laser. The laser is, however, a relatively easy one. You can just buy it. And this laser, with slight modifications, we can use to directly drive the qubit. The Hamiltonian that drives the qubit behaves like basically E star cross E of the light, which is where both E bar, or E star, and E are come from the same laser. Consequently, the dependence of the Hamiltonian that acts on the spins on the laser comes entirely through the intensity of the laser. So the Hamiltonian that manipulates the spins is an intensity of the laser multiplying something that acts as a fictitious magnetic field acting on the spins. But this field can be controlled, as you will see, using acoustic modulators, as I will show on the following slide. In this way, you can think of this Raman Hamiltonian as an optically steerable, so steerable using mirrors, and addressable, as optics is addressable, but from the viewpoint of the qubits, a radio frequency drop. Radio frequency. By choosing the pulse laser, in our case, about 10 picosecond pulses with 120 megahertz repetition, this pi of t in frequency space looks like a frequency call. And that allows us to span the 12.6 gigahertz splitting without introducing very high frequency electro-optic devices. So it is very natural for talking to such a. You may be concerned that having all these phone teeth either degrades the drive or introduces some spurious shifts, but it turns out that we can essentially use it with no additional drawbacks compared to which makes it a very effective way of qubit. In order to address our qubits, we address each of them individually. And this is done by shining a pair of laser beams into the qubits. One that addresses all the qubits at the same time, and another that completes the Raman process. So one goes from the side. This is the surface of the trap. It's here shown upside down, as it is in the lab. There is the beam that is addressing all the qubits at the same time. In the other half of the Raman process, the absorption process, happens by absorbing photons from these individually addressed that become individual channels of a 32-channel acoustic modulator supplied by STM. That allows us to address and drive in parallel one, two, or all simultaneously the qubits in our system. And we will make use of that for both computing and simulations. This is in contrast to other platforms where, including ions, where addressing is pairwise. We can do it in parallel while controlling crosstalk. So the first application is we use the system to perform digital in this ZZ and single qubit case. And we made use of this in collaboration with Niklas Müller and Zora Davudi to simulate a Z2 lattice gauge theory, whose Hamiltonian is given on the left. And the ground subject to the constraint of the Gauss laws being satisfied, which is the product of these four Z operators, being satisfied at each of the vertices of the grid. So if you look at this Hamiltonian that contains plaquette X terms and contains that are magnetic-like and edge Z terms, subject to this constraint, to keep the constraint, if you want to flip the spins, you need to flip the spins at least in pairs. So if you flip, let's say, spins 1 and 2, then under 1 and 2 spin flip, you can see that actually along V, so Z spin flip of 1 and 2, you can see that the plaquette stays the same. And of course the second half commutes. So this gives the theory a Z2 gauge at the vertices as long as the Gauss laws are observed. While interesting and with topological properties, in particular, the ground state of this theory a well-known Tautoric code. It was pointed out already in the 70s that this theory is dual to a simple Ising short-range next neighbor magnetic model. And this duality is obtained by identifying the magnetic plaquette terms with operators mu that live at the centers of each plaquette. So we can express this original theory that is expressed in terms of the sigma, in terms of these mu operators, where we have these couplings of the mu's due to the electric coupling, and the magnetic coupling is just a single qubit, single spin bias field on X. In this dual formulation, the Gauss laws are naturally built in. So the particular case that we want to simulate, or that we simulated digitally, consists of 10 plaquettes with a periodic boundary condition in one direction, which I'm here representing as a torus, and fixed boundary conditions on the other two edges. In the dual formulation, this would correspond to just 10 spins with the mu operators. With the Gauss laws naturally. Now, what we want to study is not just, say, the magnetization or other property, but we would also like to study properties of the theory that include the dynamics of entanglement, and especially how the dynamics of entanglement relates to determinization in such a theory. To study the dynamics of entanglement, we need to define a subsystem. As soon as we define a subsystem, say we split it into this region A between these two dots in the region A bar, which is the remainder of the system, the complement. This duality breaks. And the detailed way how to fix it and how to restore it in the presence of cuts, and how to use the dual formulation by to explore entanglement entropy and entanglement properties with time was explored by Nicholas Miller in his work over the last years. And he provided the guide how to implement the dual theory on a digital quantum computer based on the spins in a way that would allow us to study the entanglement entropy dynamics. In the dual formulation with these cuts, one thing to keep in mind is that the Gauss laws are no longer naturally built in. They need to be explicitly put as constraints, one on each boundary. And in addition, the presence of the boundary introduces non-gauge symmetry, which H boundary Hamiltonian. So we need to evolve by H bulk plus the H boundary. And we also need, in order to introduce explicitly two spins, sigma A and sigma B, that live on the boundary in order to be able to study the subject. So if you look at the form of this Hamiltonian, it is still Ising-like, but not necessarily nearest neighbor. While the top line terms are nearest neighbor, the boundary terms include particular couplings between non-nearest neighbor spins. It is very important to maintain this structure of couplings in order to preserve the Gauss laws and preserve the gauge property theory. And this is very effectively done using a digital approach where we can perform targeted and accurate unitary gates. It also makes very good use of the connectivity, high connectivity of the ion platform, where we can, at very similar cost, implement two qubit gates, in this case, these ZZ interactions, or XX interactions between any two pair of the qubits. And so, using this with the blueprint by Nicholas, we were able on the machine and lab support by Grass Unit in my group, Tianyi Wang, we were able to map out the evolution of the reduced density matrix of the subsystem A. In order to do that, we prepare the system in random electric field eigenstates, electric field basis states that satisfy the two Gauss laws. And then we time evolve this under the H bulk plus H bulk, using 4 digital Trotter steps, which each consist of physical ZZ gates plus single qubit conditions. After the Trotterized evolution, with always keeping 4 steps for all the evolution times, measured as g times t, so the electric integration rate times time, we characterize the subsystems A and A bar by single qubit observables in 24 bases that are chosen from a unitary 2 design so as to perform Charlotte-Mason. And then a great advance that was crucial for the project was the development of a Bissoniano-Wichmann ansatz for the entanglement Hamiltonian, i.e. for the log of the reduced density matrix of the subsystems by Nicholas. And this was the crucial thing that enabled us to characterize the entanglement spectrum using only 24 bases and about 750 plots for each basis. And an example of the reconstructed entanglement spectrum, so again, these phi of lambda are the eigenvalues of log of the reduced density matrix for various evolution times. I'm showing in orange the experimental data, and in black an exact calculation. With crosses is a simulated version of the calculation that takes into account the limited number of bases. So what we would expect to see in an ideal machine. We note that, of course, at 0 initial time, we should have only the single initial pure state. Of course, the reconstruction via the Schaller tomography is not perfect, which gives us with low probability, so to the -3 or below, it gives us other reconstructed. And as time evolves, we see that this artifact goes away, and the machine and the predicted Bissoniano-Wichmann ansatz with 0 noise start to really approach each other. Okay, so we can measure the entanglement spectrum. What can we get out of that? Would we, for example, look at the statistics, look for say level repulsion in the entanglement spectrum? But before we can do that, we need to take care of the fact that there is still an underlying symmetry that remains. And if we want to look at the statistics, say look for level repulsion, thermalization, then we need to take care of these symmetries by doing statistics independently for each of the symmetry subsectors. And this is done here at a particular evolution time. So for each of the different symmetry subspaces that are characterized by different eigenvalues of these operators, S1, S1 A bar, S2 and S2 A bar, all of which commute with the net Hamiltonian, we plot the entanglement spectrum here. And then we can independently in these symmetry sectors look at the statistics. So if we do that, then we can look, for example, at the gap ratio in the entanglement spectrum. So the ratio of the gaps between the neighboring eigenvalues of the Hamiltonian. And we see that starting with the non-zero value, of course, due to the experimental errors in construction as well as errors in the ansatz, the gap ratio increases, indicating an increased disorder that hints at the thermalization of the system, that also quantitatively approaches at an average gap ratio of 0.6 that would be predicted for a Gaussian unitary ensemble that is fully normalized. This hint becomes much clearer if we actually look at the distribution of the gap ratios of the entanglement Hamiltonian, starting in region 1, evolution time is about 0.9, region 2, and region 3. So all the data for all the electric field eigenstates for all the symmetry sectors is being together. and average radicals and obtains 1, 2, and 3 respectively. And we can see a clear evolution from a rather flat distribution that is fairly consistent with the Poissonian distribution to what very solidly matches a Gaussian unitary ensemble that we would expect dynamics of a underlying stage. So this demonstrates that using a digital quantum computer, we can study not, as has been just done in previous work, the ground states of a Z2 lattice gauge theory, but we can also study highly excited states and their thermalization dynamics and obtain accurate results. Can we work with an even larger system? And what are the limitations thereof? And a second example would be, in order to work with a larger system, it is advantageous to perform simultaneous operations. If we perform simultaneous drive, that, if you remember, I showed in the system we can physically do, this comes at the cost that the resulting couplings are not as well controlled. However, this still allows us to simulate, for example, the long-range easy Hamiltonian with tunable interactions in the transverse field, as has been suggested in the 2000s. It has been done for many years, especially the So this analog approach of simulation with even chains allows one to have a 1D tunable range near power law interaction along the X basis together with the transverse field C. Here, we at Duke, in collaboration with Chris Monroe's group, we made good use of that in order to implement not a long-range easing, but a long-range XY chemistry. And the idea here is that if we apply a strong Z transverse field, then the XX coupling, the previous page, will get averaged into a combination of XX and Y. So we end up with an XXYY effective Hamiltonian. Now, what we wanted to study was the near ground state, and in fact, the order in the near ground state of this XY long range Hamiltonian. Hermann-Wagner theorem tells us that if we have a short range interaction in 1D, then at low temperatures, I close to the ground state, we should not have any long range order. There will be always a decay that prevents long range order in such a system. However, if the interaction is long range, which our easing simulation allows us to do by simultaneously from single fold the spin with the strong Z field, then for alpha less than 3, the HXY Hamiltonian should have the ground state that is characteristic with the long range of 1 order in the XY plane. So, in other words, if we compare the spins in the XY plane of two very separated spins in space, we expect them to be correlated, even though their overall orientations will fluctuate from short. And this correlation between the neighboring spins is measured by this off-diagonal order parameter CXY. So can we do this in experiment? Can we prepare such a ground state or near ground state? And the key capability that we make use of here is, again, the individual addressing together with the simultaneous application of an analog Hamiltonian. We use our individually addressed single qubit operations in order to prepare a staggered state of the nail Hamiltonian, which we also turn on at t equals 0. With time, we gradually ramp from this nail Hamiltonian towards our final XY, which, as I said, we implement having the transverse field that averages XX into XX plus Y. So here is the sample ramp that we used, and this approach, this ramp, was suggested by the group of Alexei Gorshkov and Shenshuan Gong in 2017. And so we can try this. We can try it on, say, 7 spins, which are the middle 7 out of this train that you see at the top of the screen. Initially, we look at our order parameter Cij, and we see that, of course, diagonal spins are ordered by themselves. Of diagonal, we don't see for different spins. But as we see that we build up very solid functions. Can we do it in a bigger system? Yes. In fact, what's very nice about the ion chain is just by turning on additional beams, we can grow the size of this system and explore the same physics for more spins. So here we repeat this, not for 7, but for 11. At the end of the ramp, 15, 19, and 23 spins. And up to 23 spins, in the lab, we still see that we have strong correlations. We can characterize the set of these correlations by spatially averaging the correlator between spins separated by distance L across different sites. And this spatially averaged correlator is shown here as a function of the distance between the sites for the larger system, and the full system. Fitting the decay of the correlator with the distance between the spins gives us a very statistically significant offset, hinting that we have strong long-range coordinates. I see that I have limited time, so I will just mention the implementation of expressive gates, and also mention the result on encoding. The gates that have been implemented so far, that were done for this work, including the effective analog easing interaction, are based on state-dependent forces that act on the ions. And these forces allow us to implement an effective Hamiltonian when we drive the gates that is proportional to the sum of binary XX product of operators. It was and this based on the original ideas by Milburn and Mulmer and Sorensen. Orcatz, a postdoc in the group of Chris Monroe, suggested a way how to expand this toolbox by also incorporating squeezing into the mix. So in addition to acting with state-dependent forces, Orr introduced also the idea of state-dependent squeezing. And so the idea is that we do a Mulmer-Sorensen type gate, which traces out an area in XB phase space of motion of the spin oscillators. But then we combine this with squeezing that is controlled by the third spin. So by the third spin, by squeezing the phase space, we vary this area, which is proportional to the product of the two other spins, depending on the state of spin. And that gives us a native gate Hamiltonian that contains products of multiple spins. In our case, explicitly, it's the gate, the exponent of the exponential, the effective gate Hamiltonian will be the product of the two target spins, 1 and 3, multiplied by cosh psi times identity plus sinh psi being the squeezing strength, times the spin operator of the third spin. This can be generalized to more spins and can be used, as we demonstrated, to implement either, say, products of 3-spin operators or, in general, polynomial, effective polynomial Hamiltonians. And I would encourage you to ask me more about this, and especially encourage you to think about how such effective Hamiltonians that involve multiple body interactions can be useful for simulations and computing. I will skip over for now then an application to error correct. I will highlight also an application to error correcting codes of the system, where we used a relatively large system of 19 qubits in order to implement Steen type readout of the error correcting code. And this makes the on a Baker-Shor 13 code. This makes great use of the larger system to implement 2 copies of the code, similar to what was done in the recent group, in the recent work in the Lukin group, however, fully fault tolerant, and to implement fault tolerant readout of the syndromes by mapping from our data qubit onto the second copy which is used as the syndrome readout target. And this was done in collaboration with Ken Brown and Xilin Huang, postdoc in Ken Brown's group. And remarkably, we see that compared to our previous approach at Maryland, we get 2 to 3 lower error rates, even though the system is bigger and we use more tools. And with that, I would actually end the main part of the talk and leave for questions some of the limitations and how we're looking to get around them to improve our gates. Here, I am showing the fidelity of XX gates in both the smaller 15 ion and larger 25 ion system as a function of the wait time between the start of the circuit and the end of the circuit, the end of the gates. And we're showing, and we see a strong decay with wait time. And we understand by now very well the reasons for that, and we have a new experimental approach how to fight this decay and allow both digital and analog circuits with 20 plus fully connected qubits and long simulation times. And this is work that is now led by a student of Ken Yuang, student in my group, in collaboration with Andrew Van Horn from Johnson Kim's group. And so with that, I will end with an advertisement for the Duke Quantum Center, which now has more than a dozen faculty covering both ions and Rydberg and neutral atoms, targeting quantum simulation and quantum computing with individually addressable atomic systems. So thank you.
Wonderful. Thank you for that lovely talk. Any questions from the audience? So I'll start with just a technical question. Actually, I maybe asked this at the very beginning, but you said that your trapped ion systems are room temperature. Is that actual room temp or just not superconducting temps?
The chambers and the trap are actually room temperature.
Oh, wow.
Exactly. So all the cooling for all the work that I showed here is done entirely by lasers. This does come at zeroth order drawback, which I demonstrated precisely here. So this decay of the gate fidelity with wait time, we do understand is arising due to electric field noise generated by the trap. And not technical, but due to physics of the surfaces of the trap. And this has been shown, including in the PhD thesis of Crystal Null, cooling the trap to modest cryogenic temperatures like 4 Kelvin can result in about 2 orders of magnitude decrease in this heating rate. But this error in these gates should scale as number of ions to the 6th power, very high effect, times the wait time squared times the heating rate squared. So you can drop factor of 100 right there in the heating rate, but you can also alternatively drop the T significantly by not letting the whole chain heat up for 10 to 20 milliseconds in the circuit, but rather using synthetic cooling with ytterbium-172 ions in order to cool 171 ions during the computation. Remarkably, this works without hurting the qubits. We get less than 10 to the minus 4 loss of contrast, so less than half 10 to the minus 4, 5e minus 5 error per data qubit per cooling cycle. And very recently, we have been able to solve some technical sorting problems to keep the ordering of these ions the same by using some transposition capability of these ions trap, which we're really looking forward in the next few months to make good use of this cooling, both to fix the gate problem and also to implement control dissipation for the motion. So we have all these bosonic modes, which now can be controllably dissipated.
Nice. That's very cool and very good. Any other questions from the audience? Yeah, Martin.
Hey, Marko, thank you very much. I was wondering if you could give us a little bit of insight into what you have planned for the next 2 to 3 years in these systems.
Yes. I'll mention both in my group and wider in DQC. So in my group, I am building with 2 graduate students currently. I am building a system that will combine barium 137, so featuring potential qubits, both ground and excited state, system in a similar trap at room temperature, but where the cooling can be implemented by now saving the qubits while cooling the other one, so same species. But also very importantly, this horrible scaling with the number of ions could be avoided by holding each individual ion inside of an optical lattice. So freezing them, preventing them from moving like that, using an optical lattice. And this is a technique that I had demonstrated, that had helped demonstrate. The final demonstration was right after I left a PhD group. And so I'm hoping now to make this technique relevant to QIS. The same system should also be very interesting for some networking proposals, where photons are used to quickly exchange information over a short distance within a trap. On a more mainstream thrust at DQC, Crystal Knoll, together with Chris Monroe, are leading the building of a cryogenic barium system, which will feature the same type of shelving and cooling capabilities, but will operate at 4 Kelvin. And the plan is to have 4 independent zones with individual addresses. So fight N, I had this bad scaling with N. In a chain, this is number of ions in one chain. So an approach would be to take this chain, split it in 2. And then if you want these qubits to talk to these qubits, then you can split the 2 chains and combine them, the middle ones, into a chain, into a longer chain, and then interact them. And this saves a lot of time compared to, say, a continuum, who have to do all these transpositions in order to bring the 2 qubits that need to talk to each other together. So in a large-scale architecture, I could imagine that there is an optimal number of ions per chain, and then the trains themselves are shuffled.
So just kind of follow up on that last point. So when it comes to designing algorithms for simulations, we should be looking to work with blocks and then have the edges brought together. So really thinking about model-sized volumes with a lot of interactions on the surface to be done at one particular instant, and then move back into the volumes for further evolution. So it's like a domain decomposition of the problem.
I think that would make a lot of sense and considerable speed up while still keeping fatalities compared to continuum. And I further think, or both Chris and I think that the number per block is likely to be between 25 and 40 something. Maybe for some simulations, things like this optical lattice idea. One second. Ideas like with this optical lattice may be useful for some targeted simulations.
Thanks, Dorota. Okay, so that's something we haven't really been thinking about too much, that type of domain decomposition, but I think it's really good direction. Okay.
Any last questions from the remote audience or in person? All right, if not, let's thank Marko one more time.
Thank you.
Thank you very much. It was great.
Bye.
Bye-bye.
Bye, thank you.
Bye. Stop recording.
Oh, yeah.